Hello, my name is Pedro and I'm here to present our work entitled Custom Control System for Split Hopkinson Pressure Bars. I'm going to start with a brief introduction, then I'm going to talk about the Split Hopkinson Pressure Bar, namely regarding its working principle and our upgrade goals. Afterwards, I'm going to show you the pneumatic and electronic circuits that we implemented, and I'm going to finish off with a few conclusions. Ice strain rate testing of composites and other high-performance materials is of great interest for design engineers, in part due to their use in the aviation and aerospace industries. A common approach for these tests is the use of the Split Hopkinson Pressure bar apparatus. However, manually obtaining a consistent firing pressure in the pneumatic variation of the bar can be difficult, and the obtained repeatability is always lower than with automated procedures. Additionally, data can be lost to improper manual triggering or phantom trigger signals, wasting valuable specimens and time. And, when using the IC, the obtained results have to be manually synchronized in a somewhat difficult and time-consuming operation. Therefore, our objective is to improve the usability and repeatability of our Split Hopkinson pressure bar experiments by implementing an automated control system with trigger signals for data acquisition. In a straightforward way, how does a Split Hopkinson pressure bar work? There are two main variants, for tension and compression respectively, but both work in a very similar way, by analyzing the strain measured in the incident and transmission bars. These correspond to the ones where the strain gauges are shown in the image. After firing the strikers, there is a strain wave passing through the incident bar. This wave then affects the specimen, breaking it. Part of this wave proceeds to the transmission bar, and the rest is reflected back to the incident bar. By analyzing these three waves, we can obtain the stress that the specimen was subjected to. Our goal in this is to develop a controller that is capable of firing the mechanism at a user-defined pressure set from the computer, as well as provide a trigger signal for the illumination and high-speed camera. This signal is recorded by the same DAC as the previously mentioned strain curves. Therefore, we will have not only the previously mentioned strain curves, but also a synchronization reference point in the form of a TTL pulse at the firing instant. The relative position of the trigger pulse and the remaining curves allow us to accurately reference the DIC image to the DAC results, and thus avoid the manual positioning of the image data in respect to the bar strain curves. In order to implement this system, we first started by looking into the pneumatic circuit of the setup. The original pneumatic circuit included an analog pressure gauge, as well as a total of 4 valves, some of which with noticeable wear. Therefore, we upgraded the circuit. We kept the same firing mechanism, comprised of a 2-2 valve and reservoir. We added a new digital pressure gauge with LCD and voltage output for a controller, one 3-2 valve to control feeding, and one 5-3 valve with closed center to control the pressurization and trigger the 2-2 valve for firing. This allows us to simplify the pneumatic circuit by using a smaller number of components, taking less space but also reducing air leaks. Additionally, it also allowed us to replace some valves that were closer to end of life. Regarding the electronics development, the controller was implemented using a DSP from microchip technology, which is connected to a computer using an USB adapter exposing a COM port on the computer. Through a developed user interface, it is possible to configure the output pulses, select the target pressure, and start the procedure. This in turn starts timer 4 and its associated control loop, which is responsible for reading the pressure sensor using the ADC module, controlling the valves using GPIO pins, and, when the target pressure is reached, trigger the corresponding valve and output to sync signals using the output compare module. The electropneumatic interface is very simple. The chosen pressure sensor includes an analog output from 0 to 10 volts, which only has to be scaled to the microcontroller's 0 to 5. The valve control is made using logic N-channel MOSFETs positioned on the low side in order to be controllable with 5V TTL inputs. This is a photo of the developed controller. The pressure sensor is connected to its pin header. The connection with the computer is performed using a mini USB cable, as the converter is embedded in the board. The valves are controlled with GPIOs that are hidden behind the BNC connectors, first passing through a different board where the MOSFETs reside. The BNC connectors provide these two independent trigger outputs for high-speed cameras and illumination systems. Here we have a very simple video of the firing mechanism in operation. After firing, the system reports the actual pressure at the time of the shot. To conclude, a custom control system for our Split Hopkinson Pressure bar setups was developed based on custom electronics. The pneumatic circuit was designed to use a smaller number of components, taking less space and reducing air leaks. The system is capable of pressurizing the reservoir autonomously and firing the striker bar at the correct pressure with user-definable accepted accuracy. It implements two user-configurable outputs, triggered right after firing, for use with image acquisition and illumination systems. Thank you, and if you have any questions, feel free to ask.